Something has already been found. It wasn't announced with fanfare or broadcast across every television screen on the planet. It didn't arrive the way world-changing discoveries are supposed to arrive, with press conferences and celebration, and the triumphant feeling that humanity has taken another step forward. Instead, it came quietly, buried inside data sets and telescope readings and particle collision results, the kind of information that most people never see and wouldn't know how to interpret if they did. But the scientists who saw it understood immediately that something was wrong. Not wrong in the sense that an experiment had failed or a calculation had been mistyped. Wrong in a far deeper, far more disturbing sense. Wrong in the sense that the universe itself appeared to be behaving in a way it was never supposed to behave. And once you understand what they found, once you truly sit with the implications of what these numbers and these observations actually mean, you will never be able to look at the world around you the same way again. You are sitting wherever you are right now, and the room around you feels solid. The walls are where they should be. The light coming through the window behaves the way light is supposed to behave. If you reach out and touch a surface, you feel resistance, texture, temperature. The world presents itself to your senses as something real, something stable, something governed by rules that have been there since the beginning and will be there long after you are gone. This feeling of solidity, of permanence, of a universe operating according to fixed and knowable principles. This is not just a psychological comfort. For centuries, it has been the bedrock assumption of science itself. The belief that reality is something we can understand, something we can measure, something that will reveal its secrets if we ask the right questions in the right way. That belief has driven every great scientific achievement in human history. And right now, in laboratories and observatories and theoretical physics departments around the world, that belief is quietly coming apart. To understand why what has been discovered is so deeply unsettling, you first need to understand what we thought we knew. You need to feel the weight of the certainty we had built, because only then can you understand what it means to watch it crack. For the past 400 years, since Galileo first pointed a telescope at the night sky and Newton first wrote down his laws of motion, humanity has been constructing an increasingly detailed and increasingly confident picture of how the universe works. It is a picture built on mathematics and observation, on experiment and verification, on the slow accumulation of evidence that has been tested and retested by thousands of independent minds across generations. It is, by any measure, the most successful intellectual project in human history. At the foundation of this picture lies a simple but powerful idea. The universe operates according to laws, not laws in the human sense, not rules that can be broken or rewritten when they become inconvenient, but something deeper and more absolute. Mathematical relationships that govern every interaction between every particle and every force in the cosmos. These laws do not care who you are, or where you come from, or what you believe. They apply everywhere, at every scale, at every moment in time. A stone falls here, the same way a stone falls on the other side of the planet. The speed of light in a vacuum is the same whether you measure it in a laboratory in Switzerland or in a galaxy 10 billion light years away. This universality, this sense that reality plays by consistent rules, is not just a scientific assumption. It is the thing that makes science possible in the first place. It is the invisible ground beneath every equation, every experiment, every discovery. And for a very long time, this ground held firm. The laws of thermodynamics told us how energy moves and transforms. Maxwell's equations described electricity and magnetism with breathtaking precision. Newton's gravity explained the motion of the planets, the tides, the fall of every object on the surface of every world. These were not approximations or guesses. They were exact, verifiable, reproducible truths about the nature of reality. When you fired a cannonball at a known angle with a known force, Newton's equations told you exactly where it would land, and it would land there, every single time. When you wound up a clock, the principles of mechanics could tell you, down to the second, how long it would keep ticking. The universe, it seemed, was a machine. Complex and vast, yes, but ultimately comprehensible, ultimately knowable. Then came Einstein, and the machine became stranger. Special relativity told us that time is not the fixed, universal backdrop we had assumed it to be. Instead, time is elastic. It stretches and compresses depending on how fast you are moving and how strong the gravitational field around you is. Two clocks that are perfectly synchronized will tell different times after one of them has been accelerated to near light speeds. Time passes more slowly near a massive object like the Earth than it does in open space. These revelations were profoundly counterintuitive, but they were not destabilizing in the deepest sense because they came with a new set of equally precise, equally testable laws. The universe had become stranger, but it had not become unknowable. Einstein had simply handed us a more sophisticated machine, one in which space and time were woven together into a single, four-dimensional fabric called space-time, and in which massive objects like stars and planets warped that fabric the way a heavy ball warps a rubber sheet. It was strange, but it was beautiful, and it worked. Then came quantum mechanics, and the machine became stranger still. Here was a theory that described the behavior of matter and energy at the smallest scales, the behavior of atoms, electrons, photons, the fundamental building blocks of everything, and what it described was nothing short of bizarre. At the quantum level, particles do not have definite positions or definite velocities until they are observed. They exist instead in what physicists call a superposition, a smeared-out cloud of probability, potentially everywhere at once. Collapsing into a specific location only when measured, two particles can become entangled, their fates linked in such a way that measuring one of them instantly affects the other, regardless of the distance between them. This is not a matter of hidden information or incomplete knowledge. The uncertainty is not a gap in our understanding. According to quantum mechanics, it is the actual nature of reality at the subatomic level. The universe at its foundations does not behave deterministically. It behaves probabilistically. And yet, and this is the crucial thing, it worked. Quantum mechanics is, by the standard measure of predictive accuracy, the most successful scientific theory ever created. Its predictions match experimental results to an astonishing degree of precision. The strange, probabilistic, observer-dependent world it describes is apparently real. So by the early 21st century, humanity had constructed two towering, extraordinarily successful frameworks for understanding reality. General relativity described the universe at the largest scales, the motion of planets, the geometry of space-time, the expansion of the cosmos. Quantum mechanics described the universe at the smallest scales, the behavior of subatomic particles, the nature of light, the structure of atoms. Both frameworks were verified to a degree of precision that bordered on the miraculous. Both had survived every experimental test that had been thrown at them, and both, it turned out, were fundamentally incompatible with each other. The mathematics of general relativity breaks down at quantum scales. The mathematics of quantum mechanics, as it is currently formulated, cannot account for gravity. These two pillars of modern physics, these two supreme achievements of human intellect, describe reality in ways that cannot both be completely correct. There is a crack running through the foundation of everything we know, and it has been there for nearly a century, and we have learned to live with it, to work around it, to tell ourselves that a unified theory is coming, that it is just a matter of time before someone writes down the equation that brings it all together. That reassurance is becoming harder to sustain, because here is the thing about cracks. Once you look for them, you start to find them everywhere. And in recent years, the cracks have been multiplying, not in the subtle technical sense that physicists have quietly known about for decades, in a new, more visible, more alarming sense, in the sense that the data coming in from the most advanced observational tools humanity has ever built, from the James Webb Space Telescope, from gravitational wave detectors, from the most precise particle accelerators and cosmological surveys ever constructed, is not matching what our best theories predict. Not in small ways, not in the kind of small discrepancies that get smoothed over with a new parameter or a corrected calculation. In ways that are large enough and consistent enough and deeply enough embedded in the structure of the observations to suggest that something is fundamentally wrong with our picture of reality. Let's begin with the most concrete, most dramatic, most immediately verifiable example, because it is also the one that first alerted physicists in the most undeniable way that something was seriously amiss. It is called the Hubble tension, and to understand why it matters so much, you need to understand what physicists mean when they talk about the expansion of the universe. After Edwin Hubble's observations in the 1920s confirmed that the universe is expanding, that the galaxies are all moving away from each other, like raisins in a rising loaf of bread, it became one of the central tasks of cosmology to measure exactly how fast this expansion is occurring. This rate has a name, the Hubble constant. It is usually written as h0, and measuring it precisely is critically important because the expansion rate of the universe is connected to its age, its geometry, its ultimate fate. It is one of the most fundamental numbers in all of cosmology. For decades, measuring the Hubble constant was a matter of fierce scientific debate, with different teams using different methods arriving at different answers. But by the early 21st century, the situation seemed to be resolving. Two independent methods, each using completely different physical processes and completely different rungs of the so-called cosmic distance ladder, were converging on answers that, while not identical, were close enough to give cosmologists confidence that they were homing in on the true value. The first method used the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang, which permeates all of space and carries in its temperature variations the imprint of the early universe's conditions. By measuring these variations with extraordinary precision, cosmologists could reconstruct the entire history of the universe from its earliest moments to the present, including how fast it should be expanding today. The Planck satellite, launched by the European Space Agency, did this measurement with stunning accuracy and arrived at a value for the Hubble constant of about 67 kilometers per second per megaparsec. The second method was more direct. It used a chain of astronomical observations stretching from our own cosmic neighborhood out to the farthest reaches of the visible universe, using objects whose brightness is well understood, Cepheid variable stars, type Ia supernovae, as distance markers to directly measure how fast distant galaxies are receding from us. This measurement, carried out by teams like the one led by Nobel laureate Adam Rees, arrived at a very different answer, about 73 kilometers per second per megaparsec. That is a difference of approximately 9%, and 9% might not sound like much, but in this context, it is enormous, because these are not rough estimates or back-of-the-envelope calculations. These are measurements made with the most precise instruments in human history, refined over years and decades, checked and rechecked by independent teams. The error bars on both measurements have shrunk so small that the gap between the two values is now statistically significant to a degree that, in physics, is essentially impossible to dismiss as random chance. The two methods should be giving the same answer. They are not giving the same answer, and as far as anyone can tell, both methods are correct. You might be tempted to think of this as a technical problem, a disagreement between two measuring instruments that will eventually be resolved with better data. But the physicists who work on this problem do not see it that way, because what the Hubble tension actually represents, what it is telling us if we are willing to listen, is that the mathematical model we use to describe the entire history and structure of the universe is wrong, not slightly off, structurally incorrect. The standard model of cosmology, known as lambda CDM, lambda for dark energy, CDM for cold dark matter, is the most successful model in the history of cosmology. It accounts for an astonishing range of observations with a relatively small number of parameters. But it cannot account for both of these Hubble constant measurements simultaneously. Whatever is causing the expansion of the universe to behave the way these measurements suggest it is behaving, it is not in the model. And that means the model is, at least in some important sense, wrong. And if the model is wrong, then everything we thought we understood about the large-scale structure and evolution of the universe, the age of the cosmos, the nature of its beginning, the physics that governed its first moments, may need to be reconsidered. But the Hubble tension is only the beginning. It is the most precisely measured, most statistically robust of the anomalies, but it is not the most philosophically disturbing. To find the genuinely destabilizing discoveries, you need to go deeper, into the fabric of the universe itself, into the nature of the matter and energy it contains. And here the picture becomes not just confusing, but almost incoherent. Because when cosmologists add up everything we can see in the universe, every star, every galaxy, every cloud of gas and dust, every photon of light, we find that visible matter makes up only about 5% of the total energy content of the cosmos. 5%. The remaining 95% is something else, something we cannot see, cannot directly detect, and do not understand. About 27% of the universe, by current estimates, is composed of dark matter. This is not ordinary matter that happens to be dark, like black holes or dim stars. It is something fundamentally different, a form of matter that does not interact with light at all, that does not emit, absorb, or reflect electromagnetic radiation of any kind. We know it is there because of its gravitational effects. Galaxies rotate in ways that cannot be explained by the visible matter they contain. The outer edges of galaxies orbit the center too fast, far too fast for the gravity of the visible stars and gas to keep them in orbit. Something is providing additional gravitational pull, holding those outer stars in their orbits. That something, whatever it is dark matter. The gravitational lensing of background galaxies by galaxy clusters reveals mass far in excess of what can be accounted for by visible matter. The large-scale structure of the universe, the vast web of filaments and voids that galaxies are organized into, cannot be reproduced in computer simulations without the presence of dark matter. The evidence for dark matter's existence, inferred from its gravitational effects, is overwhelming, and yet in more than 4 decades of searching, we have not detected a single dark matter particle directly. Every dedicated experiment, underground detectors shielded from cosmic rays, accelerator searches at the Large Hadron Collider, indirect detection experiments looking for the products of dark matter annihilation, has come up empty. The most popular theoretical candidates for dark matter, particles known as WIMPs, weakly interacting massive particles, should have been detectable by experiments that are now sensitive enough to detect interactions that are almost unimaginably rare. They have not been detected. Dark matter remains, as it was when it was first hypothesized, entirely invisible, entirely undetectable, and entirely mysterious. And if dark matter is mysterious, dark energy is something else entirely. Dark energy is the name we give to the force, if it is a force, that is driving the accelerating expansion of the universe. This is perhaps the most staggering discovery in modern cosmology. Not only is the universe expanding, but the rate of its expansion is accelerating. The galaxies are not just moving apart, they are moving apart faster and faster over time, as if some invisible engine is continually adding to their velocity. This discovery, made in 1998 by 2 independent teams studying distant type Ia supernovae, earned the Nobel Prize in Physics in 2011. It is not in dispute. The universe is accelerating outward. Something is pushing it, and that something, dark energy, accounts for about 68% of the total energy content of the cosmos. We know nothing about it. We have no satisfactory theoretical framework for understanding it. The best theoretical candidate, a form of energy inherent to the vacuum of space itself, what physicists call vacuum energy, or the cosmological constant, predicts a value for dark energy that is off by a factor that varies between 10 to the power of 60 and 10 to the power of 120, depending on how you calculate it. That is not a small error. That is the most catastrophically wrong prediction in the history of physics. A prediction that is off by a factor of 10 to the power of 120 is not a rounding error. It is a signal that something is profoundly, fundamentally wrong with the way we are thinking about the relationship between quantum mechanics and gravity, about the very structure of the vacuum of space, and we do not know what it is. Take a moment to sit with this. You are living in a universe where 95% of what exists is completely unknown to us, where the most abundant constituent of the cosmos, this dark energy that is literally driving the expansion of everything, cannot be explained by any theoretical framework we possess, and the best attempt at an explanation is off by more than 100 orders of magnitude, where the second most abundant constituent, dark matter, has been inferred from its effects for more than 40 years without a single confirmed direct detection. This is not a universe where we understand the big picture and are merely filling in the details. This is a universe where our map covers 5% of the territory, and we have good reasons to suspect that the conceptual tools we are using to explore the rest may not be adequate to the task, and the James Webb Space Telescope has made things worse, or rather, more interesting and more disturbing, depending on your perspective. Launched in December 2021, the Webb telescope represents the most powerful astronomical observatory ever built. Its primary mirror is nearly 7 meters across. It observes in infrared light, allowing it to peer through the clouds of dust and gas that obscure visible light views of the early universe. It can see farther back in cosmic time than any instrument before it, observing galaxies as they existed less than 300 million years after the Big Bang, less than 2% of the current age of the universe. When the first Webb images came back and scientists analyzed the galaxies they contained, they expected to see what the standard cosmological model predicted: small, irregular, primitive proto-galaxies in the process of assembly, the raw material from which the large, organized structures we see in the later universe would eventually form. What they found instead was deeply unexpected. The early universe contained massive, fully formed galaxies, large, organized, mature-looking structures that should not, according to our best models of how galaxies form and evolve, have been able to exist so early in cosmic history. Some of these galaxies are so massive, so evolved, so structurally sophisticated, that their very existence appears to be impossible within the framework of the Lambda CDM model. They should not be there, but they are there, and Webb keeps finding more of them. The response from some cosmologists has been essentially that the models need to be revised, that we underestimated the rate at which galaxies could form in the early universe, that there are physical processes at play in the very early cosmos that our simulations do not adequately capture. This may be true, but there is a growing sense within the community that these revisions cannot be minor adjustments, that they might require something more fundamental. Because it is not just that Webb is finding big galaxies early, it is that these galaxies are systematically too big, too organized, too structured, in a way that suggests not a small quantitative error in our models, but a qualitative misunderstanding of how the early universe worked. And when you add this to the Hubble tension, to the dark matter problem, to the dark energy catastrophe, when you start to see all of these anomalies together, as a pattern rather than as isolated puzzles, a more unsettling possibility begins to take shape. What if the problem is not with our measurements? What if the problem is not even with our models? What if the problem is with the deeper assumptions that underlie all of our models, the foundational beliefs about the nature of space, time, causality, and existence that we have never seriously questioned because they seem so obviously, so self-evidently true? This is the question that is beginning to haunt the edges of theoretical physics. Not the comfortable question of which model needs revision, but the genuinely frightening question of whether we are even asking the right questions, whether the conceptual framework through which we see the universe is so limited, so deeply wrong, that no amount of model tweaking will ever be sufficient to close the gap between our theories and what the universe is actually doing. To see how destabilizing this question truly is, you need to go back to quantum mechanics, to the behavior of matter and energy at the smallest scales, and look at what it is actually telling us. Because quantum mechanics is not just strange in a superficial way. It is strange in a way that, if you take it seriously, challenges the very concept of an objective, observer-independent reality. Consider the famous double-slit experiment. You fire particles, electrons, photons, even large molecules, at a barrier with two narrow slits in it. On the other side of the barrier is a detector screen. When you send particles through this setup without measuring which slit each particle goes through, the pattern that builds up on the detector screen is not what you would expect from a stream of particles, two bands of impacts corresponding to the two slits. Instead, you get an interference pattern, alternating bands of high and low impact density, the kind of pattern you would get if waves were passing through both slits simultaneously and interfering with each other. This makes sense if particles are actually waves, or if each individual particle somehow passes through both slits at once as a wave of probability. But here is where it becomes truly strange. The moment you add a detector that measures which slit the particle goes through, the moment you introduce any physical mechanism that makes it possible, even in principle, to know which path the particle took, the interference pattern disappears. The particles start behaving like particles again, creating two bands on the detector, as if they are now going through one slit or the other, but not both. The act of measuring, of gaining information about the particle's path, changes the physical outcome. Not because the measuring device is physically disturbing the particle in some obvious mechanical sense. The effect persists even when the measurement is made with the most delicate possible means, even when the measurement is made after the particle has already passed through the slits. The knowledge of which path was taken is what matters. And the universe arranges itself differently depending on whether that knowledge exists. This is not a matter of interpretation or philosophical preference. This is the empirical result. It has been tested in thousands of different experimental configurations across decades by independent laboratories around the world with progressively greater levels of sophistication and precision. The double-slit experiment is just the most famous and easily described version of a much broader and more deeply verified phenomenon. At the quantum level, observation, measurement, interaction with information plays a constitutive role in determining the state of physical systems. Reality, at the quantum scale, is not simply there, waiting to be discovered. It comes into a definite state through interaction with other systems. Before that interaction, it exists only as a superposition of possibilities. The question that this raises, the question that has been argued about since the 1920s and that is still unresolved today, is what this actually means. What is the nature of the superposition? When a particle is in a superposition of two possible positions, what is actually going on physically? Is the particle somehow genuinely in both positions at once, spreading out through space as a real wave until it is observed? Is there something about consciousness or observation that plays a special role in determining what is real? Or are there, as the many worlds interpretation suggests, parallel branches of reality, corresponding to every possible outcome of every quantum event, all of them equally real, branching constantly and inexhaustibly through time. These are not questions at the periphery of quantum mechanics. They are questions about its core meaning, and they remain genuinely, substantively unanswered after a century of argument. The most that can be said with confidence is that whatever the quantum world is, it is not like the classical, solid, objective world of our everyday experience. The classical world of tables and chairs and planets and people, the world that feels real to you right now, is in some deep sense an emergent approximation, a kind of average or shadow of a more fundamental quantum reality that does not in itself have the properties of definiteness and locality and objectivity that we take for granted in our experience of the macroscopic world. And here is where the most recent discoveries become genuinely alarming in a philosophical sense, not just a technical one, because in the last 2 decades, experiments testing the nature of quantum entanglement have closed what were once called the loopholes in the experimental tests of Bell's theorem, and the results of those tests have implications that most people, even most educated people, have not fully absorbed. John Bell was a physicist who, in 1964, derived a mathematical inequality, now called Bell's inequality, that any theory with certain, very general and seemingly reasonable properties would have to satisfy. The properties in question are locality, meaning that physical influences cannot travel faster than light, and realism, meaning that physical systems have definite properties independent of whether they are being observed. These seem like the minimum reasonable requirements for a theory of reality. A theory that violates locality would require faster-than-light influences. A theory that violates realism would require that objects do not have definite properties when no one is looking at them. Bell showed that these two assumptions together lead to a mathematically provable constraint on the correlations between measurements of entangled particles, and that quantum mechanics predicts violations of this constraint. Experiments testing Bell's inequality have been conducted since the 1970s, with progressively tighter controls and fewer loopholes. The most rigorous tests conducted in recent years by multiple independent teams have now definitively shown that Bell's inequality is violated, exactly as quantum mechanics predicts. This result has been confirmed so thoroughly and at such high statistical significance that it is no longer seriously in doubt. What this means is that at least one of Bell's 2 assumptions, locality or realism, must be wrong. Either physical influences can act instantaneously across any distance, violating the constraint that nothing can travel faster than light, or physical systems do not have definite properties independent of measurement, or both. There is no way to interpret reality that preserves both locality and realism simultaneously. The universe, at its most fundamental level, violates at least one of these properties that we have always treated as self-evident. The world is either not locally causal or not objectively real, or some combination of both, and we do not know which. The 2022 Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their experimental work in this area, for the experiments that established beyond reasonable doubt that nature violates Bell's inequality. Read that again. The Nobel Prize in Physics was given for proving that the universe violates either local causality or objective reality, 2 properties that most people, including most scientists in other fields, would have considered the bedrock of a sensible physical world. This is not a fringe result. This is not a controversial or disputed finding. It is recognized by the highest scientific authority in the world as one of the most important discoveries in the history of physics, and its implications, that reality, at its most fundamental level, is either non-local or not objectively real in the way we have always assumed, have not been incorporated into the way most people think about the world. They should be, but even this, even the violation of Bell's inequality, with all its disorienting implications, does not fully capture the depth of the crisis, because the crisis is not just about quantum mechanics. It is about the relationship between quantum mechanics and the world we experience, and why the strangeness of the quantum world doesn't seem to manifest at the scale of everyday life. Why don't you experience yourself in a superposition of being in 2 places at once? Why does the cat in Schrödinger's famous thought experiment end up either alive or dead, rather than in a superposition of both? The standard answer, decoherence, explains how quantum superpositions effectively dissolve when a system interacts with its environment, causing the quantum possibilities to sort themselves into what look like classical definite outcomes. But decoherence does not fully resolve the philosophical puzzle. It explains why we don't observe superpositions, but it doesn't fully explain why one definite outcome occurs rather than another, or what happens to all the other possibilities. The measurement problem, the problem of how quantum possibilities become classical actualities, remains one of the deepest unsolved problems in all of physics. Now add to this another, even more recent development that has been quietly transforming the conversation about the nature of reality at its deepest levels. It comes from an unexpected direction, the study of black holes and the information paradox. When matter falls into a black hole, what happens to the information encoded in that matter? The arrangement of its particles, their quantum states, their history. Classical general relativity says that once matter crosses the event horizon, it is gone forever, eventually converted into the thermal radiation that Hawking showed black holes emit as they slowly evaporate. But quantum mechanics says that information cannot be destroyed, that the quantum state of a system always evolves in a reversible, information-preserving way. These two requirements are directly, fundamentally incompatible. One of the two greatest theories in physics must be wrong about this. And in recent years, theoretical physicists have made progress on this problem through a line of reasoning that is, if you follow it to its logical conclusion, one of the most reality-dissolving ideas ever seriously entertained. The work began with a remarkable mathematical discovery: the relationship between certain theories of gravity and curved spacetime and certain quantum field theories on the boundary of that spacetime, a correspondence known as the ADS-CFT duality. This correspondence, conjectured by Juan Maldacena in 1997, is one of the most important and most studied results in theoretical physics of the past 3 decades. What it suggests, and the word suggests, is doing a lot of work here, because the full implications are still being worked out, is that a gravitational theory in a region of space can be completely equivalent to a quantum field theory, with no gravity defined on the boundary of that region. The physics inside the volume can be fully captured by the physics on its surface. This is a specific mathematical realization of what has come to be called the holographic principle, the idea that the information content of a region of space can be encoded entirely on its boundary, that a 3-dimensional physical reality can be, in a precise mathematical sense, equivalent to a 2-dimensional description. Reality, including space itself, including the dimension of depth, may be in some sense a holographic projection. The word holographic here is often misunderstood. It does not mean that the world is a fake, that nothing is real, that we are living in a kind of video game. The holographic principle is a statement about information and encoding, about how the degrees of freedom that describe a physical system scale with area rather than volume. It is a deep mathematical result, not a metaphysical claim. But when you sit with what it actually means, when you really think about the possibility that the 3-dimensional space you are moving through right now is not a fundamental feature of reality, but an emergent property of a more fundamental 2-dimensional description, something shifts. The solidity of space itself begins to feel provisional. The depth of the room around you begins to feel like something that might be less basic than it appears. And this is precisely the direction that some of the most significant recent theoretical work has been moving. The question of whether space, not just space-time curvature, not just the geometry of the universe, but space itself, the dimension of depth, the 3-dimensional volume that objects exist in, is a fundamental or emergent feature of reality, is one of the most actively discussed questions in quantum gravity research. Several theoretical frameworks suggest that space is not fundamental, that it emerges from something more basic, just as the concept of temperature emerges from the collective motion of individual molecules without any individual molecule being hot or cold. The candidate for what space might emerge from is, in various versions of this idea, quantum entanglement. The web of quantum correlations between microscopic degrees of freedom might itself be the fabric from which the geometry of space is woven. If this is correct, and there is serious, peer-reviewed theoretical work suggesting it might be, then the space you are moving through right now, the 3-dimensional arena in which all of physical reality seems to take place, is not a fundamental thing. It is a collective phenomenon, an emergent structure as real in everyday terms as temperature, but no more fundamental. Take a breath. You are still in the same room. The walls are still where they were, but consider what you are being asked to think about. Not just that the universe is strange at microscopic scales, not just that our models need updating, but that the very arena in which you exist, the 3-dimensional space that contains your body, your chair, your building, your planet, might be an emergent, derived phenomenon, rather than a basic feature of reality. that the depth you see when you look across the room might be, in a sense that is mathematically precise and scientifically serious, something that arises from something more fundamental that itself has no spatial extent. This is not science fiction. This is not a fringe theory. This is a serious working hypothesis at the frontier of theoretical physics, supported by some of the most mathematically sophisticated work in the field, pursued by researchers at the most prestigious universities and research institutions in the world. But perhaps the deepest crack of all, the one that, when you understand it fully, makes everything else seem like a symptom of something even more fundamental, is the problem of time. We experience time as the most basic feature of existence. Time is the dimension in which we exist, in which events unfold, in which causes precede effects and the past is fixed while the future remains open. The flow of time, the sense that there is a now, a before and an after, is so intimately woven into our experience of being alive that it is almost impossible to imagine what existence would be like without it. And yet physics, at its most fundamental level, does not include a flowing time. The equations of quantum mechanics are time-symmetric. They work equally well running forward or backward. The fundamental laws of physics do not contain a preferred direction of time. The distinction between past and future, the sense that time flows, that there is an arrow to temporal experience, is not something that appears in the fundamental equations. It appears to be emergent, arising from the statistical properties of large numbers of particles, from the increase of entropy that we call the second law of thermodynamics. But the second law of thermodynamics is a statistical tendency, not a fundamental law. It says that the entropy of a closed system tends to increase over time. It does not say that time itself flows. The flowing of time, the visceral, immediate, undeniable sensation that you are moving forward through a dimension that goes from past to future, has no clear counterpart in the fundamental equations of physics. Some physicists have concluded from this that time, like space, is not fundamental, that the universe at the deepest level is a timeless structure, a kind of four-dimensional block in which all moments in time exist simultaneously, the way all points in space exist simultaneously. In this view, the experience of time flowing is a kind of cognitive illusion, a story that your brain constructs by comparing earlier and later states of memory, but not an accurate description of the nature of reality. Other physicists find this conclusion deeply troubling and unacceptable, because it seems to eliminate not just the flow of time, but causality itself, the sense that earlier events bring about later ones, that there is a meaningful direction to the arrows of cause and effect that organize our understanding of everything. Without a fundamental time, without a real distinction between past and future, the very concept of causality, the idea that things happen because of prior things, that the universe has a history, that science itself is possible because effects reliably follow causes, becomes deeply problematic. And yet it is not as if the physicists who argue for a timeless fundamental reality are being careless or anti-scientific. They are following the mathematics where it leads, doing what physicists are supposed to do, what science has always demanded of its practitioners, letting the evidence and the equations speak, even when what they say is deeply uncomfortable. The mathematician and physicist Julian Barber has spent decades developing a framework in which time does not exist at the fundamental level, in which the universe is better understood as a vast, static landscape of all possible configurations of matter, a landscape he calls Platonia, in which what we experience as the flow of time is simply the path our consciousness traces through this timeless structure. Carlo Rovelli, one of the founders of loop quantum gravity, has argued in accessible and widely read books that time is an emergent, approximate, relational phenomenon, that the fundamental equations of quantum gravity contain no time variable at all. That time as we experience it is something that arises only at the level of thermodynamics and entropy, at the level of the macroscopic world we inhabit, and that searching for time at the level of quantum gravity is like searching for cold at the level of individual molecules. These are not fringe figures. These are serious, accomplished physicists at the frontier of their field, and what they are telling us, what the mathematics is telling us, is that the most basic features of our experience of existence may not correspond to anything fundamental in the actual structure of reality. And if time is not fundamental, if space is not fundamental, if the three-dimensional arena in which you seem to exist is emergent rather than basic, then what is fundamental? What is reality at its most irreducible level? actually made of? This is the question that sits at the heart of the crisis, and the answer, or rather the collection of tentative, contested, incomplete answers that currently exist, is as disturbing as anything else in this story. Because what the most serious theoretical work seems to be converging toward is the suggestion that what is fundamental is not matter, not energy, not even space-time, but information, relationships, patterns of correlation between abstract degrees of freedom that have no obvious physical interpretation, no obvious connection to the everyday world of things and places and moments. The physicist John Archibald Wheeler, one of the great figures of 20th century physics, coined the phrase "it from bit" to express this idea, that every physical thing, every it in the universe, derives its existence from information, from binary choices, from yes or no answers to questions about the quantum state of the world. In this view, the physical world is not the ground floor of reality. It is something that emerges from a more fundamental informational substrate that is itself non-spatial, non-temporal, and quite unlike anything in our ordinary experience. The physicist Max Tegmark has pushed this idea to its most radical extreme in what he calls the mathematical universe hypothesis, the conjecture that our universe is not just described by mathematics, but is mathematics, that mathematical structures do not merely model reality but are reality, that existence and mathematical existence are the same thing. If this is correct, then every possible mathematical structure exists. Every possible consistent set of equations describes a real universe, and the particular universe we find ourselves in is simply one mathematical structure among an infinite collection of equally real structures. This is perhaps the most vertiginous idea in modern theoretical physics, and Tegmark is careful to present it not as established science, but as a serious philosophical hypothesis motivated by physical considerations. But notice what it does to your sense of what is real. If reality is ultimately a mathematical structure, if the physical world is, in the deepest sense, made of abstract patterns rather than concrete stuff, then the feeling of solidity you have when you touch a surface is something of a story, a high-level description of something that, at the most fundamental level, involves no substance at all, just structure, just pattern, just relationship. But you don't need to go as far as the mathematical universe hypothesis to find your sense of reality destabilized. You can stay much closer to the empirical ground, much closer to the actual experimental and observational results, and still arrive at a picture that is deeply unsettling. Consider the implications of quantum mechanics alone, taken seriously, without any additional philosophical extrapolation. If the results of quantum experiments mean what they appear to mean, if Bell's inequality violations are genuinely telling us that reality is either non-local or not observer-independent, then the world you experience, the world of objects with definite positions and definite properties existing independently of whether anyone is looking at them, is not the fundamental reality. It is an approximation, a classical shadow cast by a quantum reality that is, by its very nature, indefinite, entangled, and observer-dependent. The table in front of you is not, at its most fundamental level, a thing with definite properties existing in a definite place. It is a collective behavior of an enormous number of quantum systems whose individual states are indefinite and whose correlations are non-local. The apparent solidity, the apparent definiteness, the apparent locality of the macroscopic world, these are emergent features that arise from the averaging out of quantum indefiniteness over vast numbers of particles. They are real in the sense that temperature is real. They are not real in the sense that the quantum states of individual particles are real, and we do not have a complete, consistent, agreed-upon account of the relationship between these two levels of description. Now here is where the narrative shifts in a direction that many scientists find uncomfortable, but that an increasing number are beginning to take seriously. The discoveries we have been discussing, the Hubble tension, the anomalous early galaxies seen by Webb, the undetected dark matter, the catastrophically wrong prediction for dark energy, the violation of Bell's inequality, the emergent nature of space and time. What if these are not separate puzzles, each requiring its own separate solution? What if they are symptoms of a single, deeper problem? What if they are all manifestations of the same fundamental gap between the way we are, conceptualizing reality, and the way reality actually is? This is the possibility that is beginning to haunt the most reflective thinkers at the frontier of physics, and it is a possibility that does not have a comfortable resolution. Because if the problem is at the level of our most basic assumptions, if the conceptual framework we are using is itself the source of the confusion, then no amount of model adjustment, no new particle, No revised cosmological constant will be sufficient. What is needed, if this view is correct, is something much more radical: a reconceptualization of the basic structure of reality from the ground up. There is a historical precedent for this kind of conceptual revolution, and it is instructive to look at it carefully, because it shows both how dramatically our picture of reality can change and how difficult such changes are to make. In the late 19th century, physics faced a crisis of a similar character. The classical physics of Newton and Maxwell was extraordinarily successful. It could account for an enormous range of phenomena with remarkable precision, but there were anomalies. The orbit of Mercury precessed slightly faster than Newton's gravity predicted. The Michelson-Morley experiment, designed to detect the motion of Earth through the luminiferous ether, the medium through which light was supposed to propagate, found no such motion. The radiation emitted by hot objects, blackbody radiation, could not be explained by classical physics without generating a nonsensical result, known as the ultraviolet catastrophe. These anomalies seemed minor in the context of classical physics' overall success. They seemed like puzzles to be solved within the existing framework, not signs that the framework itself needed to be replaced, but they were signs. Each of them was pointing at something that classical physics could not accommodate. And when the framework was replaced by relativity and quantum mechanics, it turned out that the replacement was not a refinement of the old picture, but a radical reconceptualization of the most basic properties of reality: the nature of space, time, matter, and energy. The anomalies we are seeing today are arguably more numerous, more severe, and more fundamentally connected to the core assumptions of our theories than the anomalies that preceded the early 20th century revolution. The ultraviolet catastrophe was embarrassing, but it did not suggest that 95% of the universe was invisible. The precession of Mercury's orbit was unexplained, but it did not require us to question whether space itself was emergent. The Michelson-Morley result was puzzling, but it did not suggest that the fundamental laws of physics might violate local causality or objective reality. The scale of what we are now confronting, the depth and breadth of the gap between what our theories predict and what the universe appears to be doing, suggests that whatever conceptual revolution lies ahead, it will be at least as radical as the one that gave us relativity and quantum mechanics, perhaps more so. And yet, despite the severity of the crisis, it has not penetrated the popular understanding of science in the way it perhaps should have. The standard picture, that we understand the laws of physics, that we have a successful standard model of cosmology, that the remaining puzzles are technical rather than conceptual, persists in textbooks, in popular science accounts, in the implicit assumptions of science communication. Physicists who work at the frontier know how deep the problems go, but the comfortable public narrative of steady scientific progress, of small gaps being filled, of a generally reliable and confirmed picture of reality, does not fully capture the situation. What the frontier actually looks like, from the inside, is considerably more chaotic and uncertain than that narrative suggests. The honest answer to the question, what is the universe made of, is, we don't know. The honest answer to the question, what is the nature of space and time, is, we don't know. The honest answer to the question, what happened at and before the Big Bang, is, we don't know. And the honest answer to the question, is our current conceptual framework adequate to answer these questions, is, probably not. There is something else, something more personal, more intimate, more immediately disturbing, that needs to be said about what these discoveries mean for our understanding of ourselves. Because the questions raised by the frontier of physics are not just questions about the large-scale structure of the cosmos or the microscopic behavior of particles. They are questions about the nature of experience itself, about the relationship between the physical world and the conscious beings who observe it, about what it means to be aware of reality, when reality itself is turning out to be something so much stranger than awareness has ever been able to grasp. You are, among other things, a biological organism. Your brain is a physical system, made of neurons and synapses, governed by electrochemical processes, embedded in a body that is embedded in an environment that is embedded in a universe. Your experience of the world, the colors you see, the sounds you hear, the sense of being a continuous self moving through time, is, from a neuroscientific point of view, a construction, not a fabrication, not a lie, but a model. A representation built by your brain from the raw data of sensory input, shaped by memory and expectation, and the evolved priorities of biological survival. Neuroscience and cognitive science have been telling us this for decades. Your brain does not give you direct access to reality. It gives you a model of reality, a representation, a controlled hallucination calibrated to be useful, rather than accurate. The colors you see are not properties of the electromagnetic waves entering your eyes. They are categories invented by your visual cortex, different for different species, absent in certain perceptual disorders, potentially radically different from the way any other conscious being experiences the same physical input. The solid surfaces you feel when you touch objects are not two solid surfaces in contact. They are electromagnetic repulsion between electron clouds, interpreted by your nervous system as tactile solidity. The sense of moving forward through time is, as we have already discussed, not a direct perception of a fundamental feature of reality, but a construction of your brain's memory and prediction systems, a narrative imposed on a sequence of static neural states. The world as you experience it is, in a deep and rigorous sense, a model, and the question of how accurately that model corresponds to whatever is actually out there, to the mathematical structures or informational relationships or quantum fields or whatever turns out to be the real substance of reality, is a question to which we do not have a reliable answer. This is not a new idea. Philosophers have been exploring the gap between perception and reality since ancient Greece. Plato's allegory of the cave, the image of prisoners chained in a cave, seeing only shadows cast on the wall by objects they cannot directly observe, taking the shadows for reality, is one of the oldest and most resonant metaphors in the Western philosophical tradition. Immanuel Kant argued that the world as we experience it, the world of space, time, and causality, is shaped by the structure of our cognitive apparatus, not simply given by the world as it is in itself. The thing in itself, for Kant, is forever beyond our reach. We can only know phenomena, the world as it appears to a mind structured in the way human minds are structured. These are not obscure philosophical positions. They are serious, carefully argued responses to a genuine and deep problem, the problem of understanding what our access to reality actually amounts to and what its limits might be. What is new? What makes the current moment different from any previous moment in the history of these questions is that science itself is now arriving at conclusions that echo these philosophical concerns, not through abstract reasoning alone, but through hard experimental and observational data. The violation of Bell's inequality is not a philosophical argument, it is an experimental result. The failure of our models to account for 95% of the universe is not a conceptual puzzle, it is an empirical fact. The unexpected discoveries of the James Webb Space Telescope are not theoretical anomalies. They are photons that actually traveled 10 billion light-years to fall on a detector and form an image that contradicts our expectations. The crisis at the frontier of physics is not a matter of philosophical taste or interpretive preference. It is a crisis generated by data, by the universe refusing to behave the way our best theories say it should, and that makes it different and more urgent and more unsettling than any purely philosophical challenge could be. Let's go further down this path, because it gets stranger still. In 2019, a paper was published that has since generated enormous discussion and controversy in the physics community. It reported an experiment designed to test a thought experiment first proposed by Erwin Schrödinger's intellectual heir, the physicist Eugene Wigner, in 1961. The thought experiment, known as the Wigner's friend paradox, is a version of the measurement problem taken to its logical extreme. Wigner imagines a friend performing a quantum measurement inside an isolated laboratory. From the friend's perspective, the measurement has a definite outcome. She observes the particle to be in a specific state. But from Wigner's perspective, outside the laboratory, the friend and the particle together form a quantum system that is in a superposition. The laboratory as a whole is in a superposition of different outcomes until Wigner himself performs a measurement on the entire system. This seems paradoxical. Can it be that the friend has a definite experience of a specific outcome while simultaneously, from Wigner's perspective, no definite outcome has occurred? The thought experiment was considered a philosophical curiosity for decades, but recent advances in quantum optics have made it possible to perform actual experimental tests of the extended version, and the results suggest that in at least some interpretations, different observers can genuinely have contradictory, irreconcilable accounts of the same physical reality, and both accounts can be, in the quantum mechanical sense, correct. This result strikes at something we have always taken for granted, that there is a single, shared reality that all observers agree on, that the results of experiments are objective facts that exist independently of the perspective of whoever is doing the measuring, that science, with its commitment to intersubjective agreement and reproducible results, gives us access to a reality that is the same for everyone. What the Wigner's friend experiments suggest, what quantum mechanics, taken seriously without the comfort of classical assumptions, appears to imply, is that this picture of a single, shared, observer-independent reality may be an idealization that breaks down when pushed to its limits. Different observers can, in a quantum mechanically consistent way, have different realities, not different perspectives on the same reality, different realities. The physicist Carlo Rovelli has developed this idea into a full interpretive framework he calls relational quantum mechanics, in which the quantum state of a system, including the outcomes of measurements, is not absolute but relational. It is defined only with respect to a particular observer or system. There is no view from nowhere, no God's eye perspective from which all measurement outcomes are simultaneously definite. Every physical fact is a fact for some system, relative to some other system. Reality, on this view, is not a collection of objects with absolute properties. It is a web of relationships, each relationship real with respect to the systems it connects, but without any absolute, observer-independent truth underlying them all. This is a coherent, mathematically precise framework. It resolves many of the paradoxes of quantum mechanics, and it is, philosophically, one of the most radical pictures of reality ever seriously proposed by a mainstream physicist. It says, with full technical rigor, that there is no such thing as the way the universe is. There are only the ways the universe is relative to each possible observing system, and these relative truths need not be mutually consistent. And if you have been following this narrative and feeling increasingly destabilized, that is entirely appropriate, because what we are circling around, what all of these discoveries and theoretical developments are converging on, is something that human minds are genuinely not well equipped to process. We are evolved biological organisms. Our brains were shaped by millions of years of natural selection to navigate a world of medium-sized objects moving at medium speeds in a gravitational field of medium strength. The cognitive machinery we carry, the intuitions, the heuristics, the basic conceptual categories through which we parse the world, was built for survival, not for truth. It was built to track predators and find food and navigate social relationships, not to correctly intuit the nature of quantum superpositions or the topology of higher dimensional space-time, or the relationship between entanglement entropy and spatial geometry. There is absolutely no reason to think that evolution would have equipped us with minds capable of directly grasping the most fundamental structure of reality, and there are excellent reasons to think it did not. This is a point that is often missed in popular discussions of science and consciousness. The hard problem of consciousness, the problem of explaining why there is subjective experience at all, why there is something it is like to be you rather than nothing, is usually presented as a problem about how the brain generates experience. But there is a deeper version of the problem that is rarely discussed. Even if we had a complete account of how the brain generates experience, we would still face the question of whether that experience, the qualitative, first-person, subjective inner world that you are living right now, bears any reliable relationship to the objective structure of reality. Your brain is doing something when you perceive the world. It is processing information, constructing models, generating predictions. But the model it constructs is not reality. It is a representation of reality, shaped by the peculiarities of human sensory systems, human cognitive architecture, and the particular evolutionary pressures that shaped the human lineage. The colors you see are human colors, organized around the particular color opponent channels of the human visual system. The sounds you hear are shaped by the particular frequency sensitivity of the human ear. The causal narratives you construct to make sense of events are shaped by the particular temporal resolution and sequencing preferences of the human mind. Even the most basic category of your experience, the sense that there is an objective, persistent world of things and events out there beyond your skin, is, from a biological point of view, a cognitive construction, a useful hypothesis that your brain maintains because it has proven adaptive. And now the question becomes, is this construction, this model of a solid, causal, three-dimensional, temporally ordered world, even approximately right? Not approximately right in the everyday sense, in the sense that matters for navigating your life and predicting where objects will be when you reach for them. Of course it is approximately right in that sense. But is it approximately right as a description of the actual structure of reality at any deep level? Is the model your brain is running, built by evolution for biological survival, refined by culture and language and experience, capable of representing the quantum gravitational, possibly timeless, possibly spaceless, possibly information-theoretic truth of what the universe actually is? Or is the gap between the model and the reality so vast that our normal cognitive tools cannot even form an accurate intuition of how large the gap is, there is a sobering historical analogy here. Imagine trying to explain the concept of a gene to a medieval scholar. Not the word, the concept. The idea that the body's development is governed by encoded information stored in molecules that are replicated and transmitted between generations. This concept requires not just new vocabulary, but new conceptual categories. The concept of information storage in a physical medium, the concept of molecular biology, the concept of hereditary transmission of encoded traits that were simply not available to a medieval mind. It is not that medieval people were stupid. It is that the conceptual framework available to them, the categories, the analogies, the mental tools their culture had developed, was not sufficient to even formulate the idea of a gene, let alone evaluate it. Now ask, are we in a similar position with respect to the true structure of physical reality? Is it possible that the categories available to human minds, space, time, matter, causality, existence, reality, are as inadequate to the actual structure of the universe as medieval natural philosophy was to molecular genetics? This is not a rhetorical question. It is a question that serious thinkers at the frontier of physics are actually asking. The physicist Nima Arkani Hamed, one of the most creative and influential theoretical physicists of his generation, has spoken openly about his suspicion that the ultimate theory of everything, if it exists, will not be formulable in terms of space and time at all. That space and time, rather than being the fundamental arena in which physics takes place, will turn out to be emergent concepts that appear only in an approximate low-energy description of reality, and that the more fundamental description will use concepts that are currently beyond our conceptual grasp. He has worked on a mathematical structure called the amplituhedron, a geometric object that encodes the probabilities of particle interactions in a way that makes no reference to space-time or locality or unitarity, properties that have always been considered foundational in quantum field theory, and suggested that this might be pointing toward the kind of space-time-free fundamental description he envisions. The amplituhedron is real mathematics. It gives real results. And it suggests that the physics of particle interactions can be described without space-time, which suggests that space-time is not fundamental to that physics, which suggests, again, gently but insistently, that the space and time in which you feel yourself to exist are not the bedrock of reality. Now we need to talk about something that many scientists are reluctant to discuss in public, not because it is unscientific, but because it sounds too much like science fiction. The simulation hypothesis. The idea, developed in its most rigorous form by the philosopher Nick Bostrom, that the universe we inhabit might be a computational simulation running on some form of substrate that is itself physical in some deeper sense. Bostrom's argument is not mystical. It is a straightforward probabilistic reasoning. If it is possible for sufficiently advanced civilizations to create realistic simulations of conscious beings, and if civilizations tend to create many such simulations, then the number of simulated conscious beings would vastly outnumber the number of biological conscious beings, and any given conscious being would be far more likely to be simulated than biological. This argument is controversial and has been criticized on a number of grounds. But what is significant for our purposes is not whether the simulation hypothesis is true. It is the fact that it is not obviously falsifiable by any observation or experiment we could currently perform, and the further fact that some features of our universe look, in retrospect, suspiciously computational. The quantization of energy and angular momentum, the fact that these quantities come in discrete smallest possible units, looks, from a certain angle, like the kind of discretization you might expect in a computational system. The finite speed of light, the fact that there is a maximum speed of information transmission in the universe, looks like what you might expect if the universe were running on finite computational resources with a maximum clock speed. The fact that the laws of physics are mathematical, that the universe behaves according to rules that can be captured in equations, looks, if you are already primed to think computationally, like what you would expect of a simulated system. None of these observations constitute evidence for the simulation hypothesis in any rigorous scientific sense, but they are interesting. And the fact that they are interesting, the fact that certain features of physics look more at home in a computational framework than in a purely materialist one, is itself worth noting. More relevant, perhaps, is a recent series of results in the physics of quantum error correction that has unexpectedly revealed a deep connection between the mathematics used to correct errors in quantum computers and the mathematics that describes the structure of space-time in quantum gravity. Physicists discovered that the way quantum information is distributed and protected against errors in certain quantum error-correcting codes is mathematically identical to the way information is encoded on the boundary of space-time in the holographic duality we discussed earlier. This is not a superficial resemblance. It is a deep mathematical equivalence, and it suggests that space-time, the arena in which gravity operates, the fabric of which the universe is made, can be understood as a form of quantum error-correcting code, that the geometry of space is, in a precise mathematical sense, a structure for organizing and protecting quantum information. If space-time is a quantum error-correcting code, what does that say about the nature of reality? It does not say that we are in a simulation, but it does say that the universe has a fundamentally informational character, that the geometry of space is better understood through the language of quantum information theory than through the language of matter and fields, and that is strange enough on its own. Let's step back for a moment and consider the cumulative weight of what we have discussed, because it is easy to lose track of the overall picture when moving through specific discoveries and ideas. The Hubble tension tells us that our standard model of cosmology is wrong in a way that is not accounted for by any known physics. The James Webb Space Telescope is finding galaxies that should not exist in the early universe. Dark matter and dark energy together constitute 95% of the universe and are both completely mysterious. The violation of Bell's inequality tells us that reality is either non-local or not observer-independent. The holographic principle suggests that space may be emergent rather than fundamental. The equations of quantum gravity suggest that time may be emergent rather than fundamental. Wigner's friend experiments suggest that different observers can have genuinely contradictory and mutually irreconcilable accounts of reality. And theoretical work on amplituhedra and quantum error-correcting codes suggests that space-time itself may be better understood as an informational or computational structure than as a physical arena. This is not a collection of minor anomalies. This is a wholesale unraveling of the picture of reality that modern physics had constructed, and the unraveling is ongoing. It is worth being honest about one thing at this point, because intellectual honesty is the only thing that makes any of this meaningful. Scientists disagree, significantly, about the interpretation and implications of all of these results. There are physicists who think the Hubble tension will be resolved by new measurements or improved analysis, and does not require new physics. There are physicists who think dark matter will eventually be detected directly, and is simply a new type of particle we haven't found yet. There are physicists who think the interpretation of Bell's inequality violations is more subtle than the stark non-locality or non-realism framing suggests, and that a careful analysis reveals hidden loopholes or alternative interpretations. There are physicists who find the holographic principle and the emergence of space-time compelling, but think they apply only in specific mathematical contexts and should not be taken as sweeping claims about the nature of reality as we experience it. Science is not a monolith. It is a conversation, often a heated and contentious one, populated by intelligent people with different intuitions and different judgments about which evidence is most compelling and which theoretical frameworks are most promising. But, and this is crucial, the disagreements within the scientific community are about the solutions, not about the problems. There is no serious disagreement about the fact that the Hubble tension exists and is statistically significant. There is no serious disagreement about the fact that dark matter and dark energy have not been directly characterized despite decades of searching. There is no serious disagreement about the fact that Bell's inequality is violated. There is no serious disagreement about the fact that the early universe galaxies observed by Webb are surprising and difficult to accommodate in the standard model. The anomalies are real. The cracks are real. What scientists disagree about is how deep those cracks go, whether they require minor repairs or fundamental reconstruction. And increasingly, the physicists who are most deeply engaged with the most fundamental questions are concluding that the reconstruction required is more fundamental than the mainstream narrative acknowledges. One more development needs to be brought into this picture, and it is perhaps the most philosophically charged of all. For decades, physicists have dreamed of a theory of everything, a single mathematical framework that would unify quantum mechanics and general relativity, that would derive all the known forces and particles from a single set of principles, that would answer the deepest questions about why the universe is the way it is. For much of the past 40 years, the leading candidate for this framework has been string theory, a mathematical structure in which the fundamental objects of nature are not point particles, but tiny, one-dimensional strings of energy vibrating at different frequencies, with different vibrational modes corresponding to different particles. String theory is mathematically extraordinarily rich and has generated some of the most beautiful and powerful mathematics in the history of physics. But it has also, despite decades of effort, failed to make a single distinctive, falsifiable, experimentally confirmed prediction. And the landscape of possible string theories, the number of different ways to compactify the extra dimensions the theory requires down to the 4 dimensions we observe, is estimated to be on the order of 10 to the power of 500, a number so large it is genuinely incomprehensible. Each of these different configurations of string theory corresponds to a universe with different physical laws, different constants of nature, different particles and forces. This has led some physicists to embrace what is known as the anthropic principle, the idea that we live in the particular universe we do, with the particular laws and constants it has, simply because those are the conditions under which beings like us, capable of asking such questions, can exist. In an enormous landscape of possible universes with different physical parameters, only a small subset will contain conditions compatible with the existence of complex, organized, self-aware systems. We must find ourselves in one of those universes, not because our universe's parameters were chosen for us, but simply because observers can only exist in universes that permit the existence of observers. This reasoning, known as the anthropic or observer's selection argument, allows physicists to avoid the question of why our particular physical constants have the values they do by embedding our universe in a vast multiverse of all possible universes, in which every possibility is realized somewhere. The multiverse, whatever its ultimate status as a scientific hypothesis, represents a profound shift in what science means and what it can explain. In a single universe with fixed laws, science's task is to explain why those laws are what they are, to derive them from deeper principles. In a multiverse with all possible laws, science can no longer fully explain why our particular laws are what they are, only that they are compatible with our existence. This is not the kind of explanation that science has traditionally been in the business of providing. It is a kind of explanation that some physicists find deeply satisfying and others find deeply unsatisfying. But regardless of one's feelings about it, the very fact that the multiverse interpretation of string theory is taken seriously by a significant fraction of the most accomplished theoretical physicists alive represents a remarkable shift in the ambitions and methods of fundamental physics. We may be approaching the limits of what science, as currently conceived, can explain about the universe we inhabit, and this raises the most fundamental and most uncomfortable question of all. Are there things about reality that science cannot, even in principle, ever know? Not just things that are technically difficult to measure, or that require more computing power or better instruments, things that are, by their very nature, beyond the reach of any possible scientific investigation. Candidates for such things include the nature of consciousness and subjective experience. Since science can describe the correlates of consciousness, the brain states that accompany various experiences, but cannot from the outside determine what any experience is like from the inside. The reason for the existence of anything rather than nothing, since science can describe the laws that govern the universe, but cannot explain why those laws exist or why anything at all exists that obeys them. The question of whether we are in a simulation, since by definition a perfect simulation would be indistinguishable from the simulated reality from the inside, and the question of what, if anything, exists outside the observable universe and outside the causally connected region from which we can ever receive information. These are not just philosophical distractions from real science. They are questions that arise directly from the practice of frontier physics, questions that the physics itself is pointing toward, questions that the anomalies and discoveries we have been discussing are making more, not less, urgent, and they share a common structure. They all involve limits, limits of observation, limits of inference, limits of the conceptual apparatus available to human minds, limits of what is in principle knowable from inside a physical universe with the properties ours has. The frontier of physics is not just a frontier of knowledge in the ordinary sense, a boundary that can be pushed back by more experiments and better theories. It may be a frontier in a more absolute sense, a boundary beyond which certain kinds of questions cannot be answered, not because of technological limitations, but because of the fundamental structure of how knowledge and existence are related. Consider the observable universe. The cosmic microwave background, the oldest light we can see, comes from a surface about 46 billion light-years away in every direction. That is the edge of the observable universe. the boundary beyond which no signal, no information, has had time to reach us since the Big Bang. Beyond that boundary lies what physicists call the unobservable universe, a region of space that, by definition, can never be observed from our location. We know it must exist because there is no reason to think our observable patch is special or isolated. We know that it has the same basic physics as our patch because the observable universe is remarkably homogeneous and isotropic, suggesting that it and its surroundings were in causal contact very early in cosmic history, during a period of rapid expansion called inflation. But we can never know the specific conditions beyond our observable horizon. We can never know whether the laws of physics are the same everywhere in the unobservable universe, or whether the constants of nature vary across regions too far away to observe. This is not an instrumental limitation. It is a fundamental feature of the physics of an expanding universe. It is an absolute horizon on knowledge, built into the structure of space and time itself. And if there is an absolute horizon on our observational knowledge of the universe's large-scale structure, there may be analogous absolute horizons in other domains. Quantum mechanics tells us that there is a minimum scale, the Planck scale, approximately 10 to the minus 35 meters, at which the current frameworks of physics completely break down, at which quantum effects and gravitational effects become simultaneously important in a way our theories cannot handle. What happens at and below the Planck scale? We genuinely do not know. The Planck scale is not just currently beyond our experimental reach, it is so far beyond the energies achievable by any foreseeable technology that it may be permanently inaccessible to direct experimental probing. We may be able to infer things about Planck scale physics indirectly from observations of the early universe or from mathematical constraints on the structure of possible theories. But a direct experimental window onto the fabric of space-time at the fundamental scale may never be available to us. The deepest level of reality, the level at which space and time themselves dissolve into something more fundamental, may be permanently hidden behind a veil of scale. This is a strange and troubling position to be in. We are a species that has built its greatest intellectual achievement, modern science, on the principle that reality is knowable, that patient and clever investigation can reveal the hidden order beneath the appearances. And now, at the frontier of that very achievement, we are finding evidence that this principle may have limits, that reality may have depths that are not just currently unknown, but potentially unknowable, not just technically inaccessible, but fundamentally beyond the reach of any investigation we could ever carry out. This is not defeatism. It is not anti-science. It is the honest acknowledgement of what the science itself is telling us, that the universe is not obligated to be fully legible to the particular kind of minds that happen to have evolved on one small planet, in one ordinary galaxy, in one corner of one observable region of whatever it is that actually exists. And yet, even as we acknowledge these limits, something remarkable and deeply human asserts itself. The very fact that we can identify these limits, the very fact that we can construct the mathematics to describe the Planck scale, even if we cannot experimentally access it, that we can prove Bell's theorem even if its implications remain philosophically contested, that we can detect the gravitational effects of dark matter even if we cannot identify its constituents, that we can observe the cosmic microwave background and read in it the conditions of the universe, 380,000 years after its birth. The very fact that a biological organism on a small rock orbiting an ordinary star can reach out with instruments and mathematics and thought and touch the structure of a cosmos 13.5 billion years old and tens of billions of light years across, this is itself something extraordinary, something that demands to be noticed, even in the midst of all the uncertainty and confusion. The crisis at the frontier of physics is not a story of failure. It is a story of success that has gone so far and so deep that it has begun to reveal not just the answers to our questions, but the limits of the questions themselves. But let's not let that observation become too comfortable, too reassuring, too easy. Because the specific nature of what is being discovered, not just the existence of limits, but the particular shape of those limits and the particular anomalies that are appearing as we approach them, deserves more than philosophical equanimity. It deserves genuine unease. Consider the fine-tuning problem. The physical constants of the universe, the strength of gravity, the strength of the electromagnetic force, the mass of the electron, the cosmological constant, appear to be tuned to values that are, in various ways, extraordinarily precisely adjusted for the existence of complexity and life. Change the strength of the strong nuclear force by a few percent, and stable atoms cannot form. change the cosmological constant by a tiny fraction of its observed value, and the universe either collapses immediately back on itself or expands so rapidly that matter never has time to clump into galaxies. Change the ratio of the electromagnetic force to gravity, and stars cannot form or cannot last long enough to produce the heavy elements needed for chemistry. The universe appears to be fine-tuned for the existence of complex structures. Not perfectly fine-tuned, not tuned in every way, but tuned in enough ways and to a sufficient degree of precision that it seems unlikely to be a coincidence. The mainstream response to fine-tuning, the anthropic argument embedded in the multiverse, says that this appearance of design is an illusion, that we simply cannot observe universes where the constants are different because those universes don't contain observers. But this response, while logically coherent, is deeply unsatisfying in a scientific sense, because it effectively places the explanation for the universe's fundamental parameters beyond the reach of any possible scientific investigation. If every possible combination of constants exists somewhere in the multiverse, and if we necessarily find ourselves in a life-permitting region of that multiverse, then there is nothing to explain and nothing to investigate. The fine-tuning is dissolved rather than explained, and many physicists find this dissolution inadequate, not because they want a theistic explanation or a teleological explanation, but because they believe that science should, in principle, be able to explain why the constants have the values they do. And a framework that renders this question permanently unanswerable is not a scientific explanation, but a scientific retreat. The philosopher of physics Lee Smolin has argued for a different approach, one he calls cosmological natural selection, in which universes reproduce through black holes, with each new universe having slightly different constants, and in which the constants of our universe reflect the evolutionary pressure toward universes that produce the maximum number of black holes. This is an ingenious idea, and Smolin is careful to note that it makes some predictions that are in principle testable, but it too has deep problems, and it illustrates the general difficulty of the situation. We have a genuine puzzle. Why do the constants have the values they do? And the candidate explanations range from the untestable to the highly speculative, with nothing in between that is both scientifically rigorous and genuinely satisfying. This is not a situation that science has been in before, not at this level of depth, not with this degree of pervasiveness across the most fundamental questions. Now here is something that very few popular accounts of these issues grapple with honestly, something that represents perhaps the most philosophically challenging aspect of the entire situation: the scientific method, the process of forming hypotheses, making predictions, testing those predictions against observations, and revising the hypotheses accordingly, works extraordinarily well when the hypotheses are about things that can be observed, measured, and tested. It is the most powerful tool humanity has ever developed for learning about the world. But it has a limitation that is rarely acknowledged in popular science communication. It is a method for learning about reality from the inside. It is a method for learning about the universe from the perspective of observers embedded within that universe, using instruments made of matter that is part of the universe, making measurements that are governed by the physical laws of the universe. It cannot by its nature step outside the universe and check its results against an independent standard. It cannot verify that the universe it is investigating is the only universe, or the fundamental universe, or that the laws it discovers are the deepest possible laws rather than the emergent laws of some more fundamental substrate. This is not a criticism of science. It is a description of science. All knowledge is perspectival. All inquiry is conducted from some particular standpoint, with some particular set of tools, asking some particular set of questions. The standpoint of science, the perspective of a biological organism embedded in a physical universe, using the instruments and mathematics available to that organism, is an extraordinarily powerful and productive standpoint. But it is a standpoint. And what the frontier of physics is beginning to reveal is the edges of that standpoint, the places where the perspective runs out, where the tools become inadequate, where the questions become unanswerable, not because we haven't tried hard enough, but because answering them would require a kind of access to reality that is not available from inside it. Imagine for a moment that you are a character in a novel. Everything you know about the world is contained within the pages of that novel. The world of the novel is internally consistent. It has its own history, its own physics, its own geography. You can investigate the world of the novel, learn its rules, map its geography, understand its history. You can even, through the kind of internal investigation that corresponds to doing science, discover the laws that govern the novel's world. But there are things you cannot know from inside the novel. Whether the novel is real or fictional, whether there is an author and what they intended, what exists outside the novel's world, why the novel's laws are what they are rather than something else. These questions are not answerable from inside the novel, because the novel's content cannot reach beyond itself. The novel does not contain information about its own ontological status. This is not a perfect analogy. No analogy for this situation can be perfect because the situation is genuinely novel, genuinely unprecedented, but it captures something of the epistemic position we may find ourselves in. Not because we are in a novel, not because we are in a simulation, but because we are embedded observers in a physical universe, and the nature of being an embedded observer limits, in ways that are beginning to become visible, what kinds of truths are accessible to us. Let's come back from these high philosophical altitudes and return to something more concrete, to the actual frontier of experimental physics, where things are happening right now that are generating genuine surprise and genuine confusion among practicing scientists. The field of quantum computing has in recent years been producing results that are forcing physicists to think in new ways about the relationship between information, computation, and physical reality. When Google's quantum computing team claimed to have achieved quantum supremacy in 2019, demonstrating that their quantum processor could perform a specific calculation in 200 seconds that would take the world's best classical supercomputer 10,000 years, the claim was immediately contested by IBM, who argued that the task could be done on a classical machine in 2.5 days. But the argument was not really about who was right. It was about what it means for a physical system to perform a computation. And that question leads, surprisingly quickly, into deep water, because quantum computation works by exploiting superposition and entanglement, by allowing qubits to exist in multiple states simultaneously, and to be correlated in ways that have no classical counterpart. It is essentially harnessing the quantum nature of reality to perform calculations that classical systems cannot perform efficiently. When a quantum computer solves a problem, it is not going through the possible solutions one by one, as a classical computer would. It is, in some sense, exploring many possibilities simultaneously, through a process that is fundamentally quantum mechanical. What does it mean for a physical system to explore many possibilities simultaneously? In the many worlds interpretation of quantum mechanics, it means that the computation is actually being distributed across many branches of reality, many parallel instances of the universe, with different branches exploring different computational paths, and the interference between those branches producing the quantum speedup. This is, again, not the only possible interpretation, but it is a coherent one, taken seriously by some of the most prominent quantum computing researchers, and what it says is that a working quantum computer, a device that fits in a room, that you can photograph and touch, may be a machine that computes by distributing its workload across parallel realities. If that interpretation is correct, then quantum computers are not just useful devices, they are windows onto the multiverse. They are experimental evidence that parallel realities, whatever their ultimate nature, play a physically real role in the computational processes of our universe. None of this is settled. None of this is universally agreed upon. The interpretation of quantum mechanics remains one of the most contested areas in all of philosophy of physics, but the contestation itself is significant. The fact that we have a theory, quantum mechanics, that is the most empirically successful theory in the history of science, and that we still do not agree, after a century, on what it means, on what it is telling us about the nature of reality, this fact speaks for itself. The success of the theory is not in doubt. The reality it describes, the deeper physical picture it is painting, is profoundly, stubbornly, genuinely in doubt. And that is extraordinary. That is not how science is supposed to work. You are supposed to get the right theory and then understand what it means. Quantum mechanics is the right theory, verified to extraordinary precision, and we do not understand what it means. We have learned to use it without understanding it. We have built transistors and lasers and MRI machines and quantum computers without resolving the fundamental question of what the theory is actually telling us about what exists. There is a phrase, attributed to Richard Feynman but reflecting a sentiment widely shared among physicists, that captures this situation perfectly. I think I can safely say that nobody understands quantum mechanics. This was not false modesty. It was not a poetic overstatement. It was the honest assessment of one of the greatest physicists of the 20th century, a man who won the Nobel Prize for his contributions to quantum field theory, who developed the Feynman diagram formalism that is the standard tool of particle physics, who understood quantum mechanics more deeply than almost any human being who has ever lived. He was saying, We can use it, we can calculate with it, we can predict with it, but we do not understand what it is. The machinery works. The picture it is trying to give us of reality, the deeper meaning of the waves and particles and superpositions and entanglements that we do not understand, and we still don't. Not in any way that commands general agreement. Not in any way that resolves the basic philosophical questions. Not in any way that tells us unambiguously what the quantum world is. And if we don't understand what quantum mechanics means, then in a very real sense we don't understand what matter is. We don't understand what energy is. We don't understand what the fundamental substrate of the physical world is. Everything we build on top of quantum mechanics, chemistry, materials science, solid-state physics, nuclear physics, particle physics, all of it is correct at the level of prediction and application, but all of it rests on a foundation whose nature we cannot clearly articulate. The house is built, and it is a magnificent house, but the foundation is a mystery. And now the foundation is cracking in ways that are visible from inside the house, and the cracks are multiplying, and the physicists who live in the house and have dedicated their lives to understanding it are beginning to look at each other with the quiet, unsettling recognition that something fundamental may need to be reconsidered. Let's take a step back and consider what you have absorbed in the course of this exploration, because the weight of it, the cumulative weight of these discoveries and what they imply, deserves to be felt rather than just noted. You began in a room that felt solid. The walls were where they should be. The light behaved the way light is supposed to behave. The world presented itself as something real, something stable, something governed by knowable rules. And now you are being asked to hold in your mind the following: that the universe is expanding at a rate that our best models cannot account for, that 95% of the universe is made of things we cannot see, cannot detect, and cannot explain, that the most advanced telescope in history is finding galaxies that should not exist, that the most fundamental physical theory we possess implies that reality is either non-local or not objectively real, that space and time may both be emergent rather than fundamental, that different observers may inhabit genuinely different and mutually inconsistent realities, that the equations governing the universe's deepest level may contain no time at all, that space-time may be a quantum error-correcting code, and that there may be questions about the nature of reality that are, in principle, unanswerable from inside the universe in which we exist. All of this is not speculation or science fiction. It is the current state of frontier physics and cosmology, drawn from peer-reviewed research, Nobel Prize-winning experiments, and the considered assessments of some of the most accomplished scientific minds alive. Now consider what it means to live in this moment. You are alive at the precise historical juncture when humanity's most powerful tools for investigating reality, the James Webb Space Telescope, gravitational wave detectors, quantum computers, the Large Hadron Collider, the Planck satellite, the array of underground dark matter detectors, are returning data that is systematically, persistently, and in some cases dramatically inconsistent with our best theoretical models. You are alive at the moment when the most fundamental questions in physics, what is matter, what is space, what is time, what is reality, are not receding toward comfortable resolution, but are instead becoming more acute, more pressing, more genuinely uncertain as we investigate them more deeply. This is not the twilight of science, the dying of the light of human inquiry. It is, if anything, a new dawn. But it is a dawn that rises over a landscape that looks nothing like the one we thought we were mapping. The philosopher Thomas Kuhn, in his landmark work on the structure of scientific revolutions, described the way scientific progress does not occur as a smooth, continuous accumulation of knowledge, but as a series of punctuated shifts, periods of normal science interrupted by revolutionary breaks in which the fundamental framework of a field is replaced. He called these breaks paradigm shifts. The history of science is punctuated by them. The Copernican revolution, which displaced Earth from the center of the cosmos. The Newtonian synthesis, which replaced Aristotelian natural philosophy with a mathematical mechanics. The Darwinian revolution, which replaced the fixity of species with the dynamic, undirected process of natural selection. The relativity quantum revolution of the early 20th century, which replaced classical mechanics and classical determinism with the stranger, richer, more flexible framework of modern physics. Each of these revolutions was preceded by a period of anomaly accumulation, a period in which the existing paradigm began to produce results that it could not accommodate, in which patches and adjustments multiplied and became increasingly unwieldy, in which the most sensitive practitioners began to feel that something was fundamentally wrong. We are in such a period now. The anomalies are multiplying. The patches are becoming unwieldy. The most sensitive practitioners, the physicists who work at the deepest levels of the field, who think most carefully about foundations and interpretation, are beginning to suspect that what is needed is not a better model within the existing framework, but a new framework altogether. This is exciting, in the way that all great scientific revolutions are exciting. It is the moment before the dawn, the moment of maximum confusion and maximum creative possibility, the moment when the old certainties have collapsed and the new framework has not yet been found. It is, historically, the moment when the most profound and most lasting scientific breakthroughs are made, when someone, somewhere, has the insight that cuts through the accumulated confusion and reveals the deeper structure beneath. But it is also frightening, not in the sense of physical danger, but in the existential sense, in the sense that the collapse of certainty about the nature of reality is genuinely disorienting, genuinely challenging to the basic human need for a stable, comprehensible world. The history of science tells us that paradigm shifts are always initially resisted, not out of intellectual cowardice or deliberate obscurantism, but because the old framework is not just a set of beliefs. It is a way of seeing, a set of conceptual categories so deeply internalized that they feel like the furniture of reality itself, rather than theoretical constructs. When Copernicus proposed that the Earth moves around the sun, the resistance was not just from religious authority. It was from people for whom the motion of the sun across the sky was the most obvious, direct, undeniable fact of experience. People who could not imagine what it would mean to say that this experience was wrong. When Einstein proposed that time is relative, that two observers in different states of motion experience different rates of temporal passage, the resistance was from people for whom the absolute, universal nature of time was so self-evident that the suggestion of its relativity seemed not just wrong but meaningless. In each case, the resistance was eventually overcome, not by argument alone, but by the accumulating weight of evidence, and by the gradual replacement of one generation of scientists by another that had grown up with the new framework and found it natural. What the coming revolution, if it comes, and the signs suggest strongly that it must, will replace is not just a set of physical models. It will replace the deepest categorical assumptions we make about reality, the assumption that space is fundamental, that time is fundamental, that there is a single observer-independent world, that causality is a fixed and universal structure, that the universe is made of things rather than relationships or information or mathematical patterns. These are not just scientific assumptions. They are assumptions built into language, built into the way we organize thought, built into the cognitive architecture of human minds shaped by millions of years of evolution, in a world where these assumptions are pragmatically adequate, where they work well enough for survival. Replacing them will require not just new equations but new concepts, new words, new metaphors, new ways of thinking that don't yet exist, and that will have to be invented by minds wrestling with realities for which no previous mind was prepared. This is the true depth of the challenge. It is not just an intellectual challenge, though it is certainly that. It is a cognitive challenge, a challenge to the very structure of how human minds are able to think. The physicist who finally cracks this, who finds the new framework, who writes down the new equations, who sees the deeper structure that makes the anomalies dissolve and the cracks close, will not just be doing physics. They will be doing something that is simultaneously physics, mathematics, philosophy, and a kind of cognitive revolution. They will be thinking thoughts that, in some sense, no human mind has yet been structured to think. And in doing so, they will be crossing a threshold that all previous scientific revolutions have approached but never quite reached. The threshold at which the human conceptual apparatus, developed for one kind of world, stretches itself far enough to grasp the nature of a very different kind of reality. There is something else to be said here, something that sits at the intersection of physics and consciousness, and that represents perhaps the most unsettling frontier of all, the question of consciousness itself. For all of the strangeness of quantum mechanics, for all of the mysteries of dark matter and dark energy, for all of the puzzles of the holographic universe and emergent spacetime, the most mysterious thing we know about is arguably not far away in the cosmos or hidden in the subatomic realm. It is here, inside you. The fact that there is something it is like to be you. The fact that you are not just processing information, not just computing, not just responding to inputs with appropriate outputs, but that all of this is accompanied by experience, by a qualitative inner life, by the vivid, immediate, undeniable sense of being aware. This consciousness, subjective experience, the hard problem, is, by the assessment of most philosophers and many scientists who have studied it carefully, genuinely, and deeply, unexplained. And what makes consciousness relevant to our story, what makes it not just a fascinating puzzle in its own right, but directly connected to the frontier of physics, is the following. If consciousness involves something that is not captured by the physical description of the brain, if the subjective, qualitative character of experience cannot be fully explained in terms of the objective, quantitative processes described by neuroscience, then either there is something about physical reality that we have not yet incorporated into our theories, or there is something about consciousness that lies outside the physical picture entirely. The first possibility suggests that the physics is incomplete in a way that directly affects our understanding of mind. The second possibility raises questions about the relationship between mind and reality that go far beyond neuroscience. And given everything we have discussed, given the emergent nature of space and time, the observer dependence of quantum states, the possibility that information is more fundamental than matter, the suggestion that consciousness might play a role in the deeper structure of reality, begins to seem less like mysticism and more like a serious scientific hypothesis. The physicist Roger Penrose and the anesthesiologist Stuart Hameroff have proposed a framework, orchestrated objective reduction, or ORC-OR, in which consciousness arises from quantum computations occurring in structures within neurons called microtubules, and in which the collapse of quantum superpositions in these structures is governed by a physics that is not fully captured by standard quantum mechanics, but requires a new, as yet undiscovered theory of quantum gravity. This proposal is highly controversial and has been criticized on multiple grounds by biologists, neuroscientists, and physicists, but it represents an attempt to take both the hard problem of consciousness and the quantum measurement problem seriously simultaneously, to propose that both problems might be solved by the same new physics. The proposal may be wrong. The specific mechanisms it invokes may not be the right ones. But the broader suggestion that consciousness and quantum mechanics might be connected through an undiscovered layer of physics is not obviously absurd. It is, at minimum, a coherent and interesting hypothesis. What is perhaps more significant than the specific proposal of ORC-OR is the general growing recognition that the standard approach to consciousness, explaining it as an emergent property of sufficiently complex classical information processing with no new physics required, may be too simple. The philosopher David Chalmers, who coined the phrase "the hard problem of consciousness," has argued for decades that no amount of functional or computational description of the brain will ever explain why there is something it is like to be the brain, why the information processing is accompanied by subjective experience. His argument is not that science is wrong about the brain. It is that the explanatory gap between objective physical description and subjective qualitative experience is so profound that it cannot be closed by more of the same, by better neuroscience, by higher resolution brain imaging, by more detailed computational models. Something new is needed, and whatever that something is, it will likely require a rethinking of the relationship between the physical and the experiential that goes deeper than anything in current science. Here is the thought that is perhaps hardest to hold, the thought that sits at the very bottom of everything we have been discussing, the thought that most directly confronts the comfortable assumption that we know, at some basic level, what is real. Every scientific investigation, every measurement, every observation, every experiment, all of it happens inside consciousness. Not inside any one individual's consciousness, but inside the collective human consciousness, the shared space of experience and communication within which all scientific knowledge is built, transmitted, tested, and refined. The instruments are real, the particles are real, the galaxies are real, but our knowledge of all of them arrives through experience. Through the experience of looking at detector readings, of analyzing data, of reading papers and attending conferences and following arguments. The entire edifice of scientific knowledge, everything we know about the universe, exists inside experience. And if experience itself, consciousness itself, is not fully explained by the physics we have, then we are in the peculiar position of using a tool we do not understand to investigate a reality that may not be fully separable from the tool itself. This is the most vertiginous thought of all. The observer and the observed may not be as cleanly separable as the classical scientific picture assumed. The act of observation may not be as neutral and detached as the classical picture assumed. The universe may not be as independent of the minds that investigate it as the classical picture assumed. Quantum mechanics has been hinting at this for a century. The Bell inequality violations have made it more concrete. The Wigner's friend experiments have pushed it further. And the deep unresolved problem of consciousness, the fact that we have no idea how or why physical processes give rise to subjective experience, suggests that the relationship between mind and matter may be more intimate, more mutual, more constitutive than the standard picture acknowledges, not in a mystical sense, not in a sense that abandons rigor or invites magical thinking, but in the precise technical, scientifically serious sense that the current framework may be radically incomplete in ways that directly concern the relationship between observers and observed reality. You are still in the room. The walls are still there. The light still behaves the way it always has. Your body still responds to gravity. Your heart still beats. The world still presents itself as solid and real and continuous. And yet you have now looked at what the most advanced scientific investigations in history are returning, at the data coming from the most sensitive instruments ever built, from the most sophisticated theoretical frameworks ever developed, and you have seen that the picture of reality these investigations are painting is one in which solidity is emergent, in which space and time are provisional, in which objectivity is at minimum observer relative, in which 95% of what exists is unknown, in which the universe is expanding at a rate our best models cannot explain, and in which early galaxies are appearing where our cosmology says there should be none. You have seen that the most successful scientific theory ever created, quantum mechanics, still after a century defies clear interpretation, that the two greatest pillars of modern physics are mathematically incompatible, that the most fundamental questions on what is matter, what is space, what is time, what is consciousness, remain genuinely, deeply, scientifically open. None of this means that the world is not real. None of this means that science has failed. None of this means that you should distrust your experience or abandon your understanding of everyday life. The physics of everyday life, the physics of tables and chairs and apples falling from trees, is not in doubt. It works. It will continue to work. The crisis is at the frontier, at the deepest levels of investigation, where the questions are the hardest and the answers the most uncertain. But the frontier matters. The frontier is where the truth lives, where the real structure of reality is hiding, where the gap between what we know and what is actually the case is most visible. And what the frontier is telling us, what the data is insisting on, with a persistence that is becoming impossible to ignore, is that the picture of reality we have been building for 4 centuries, the picture that has guided and informed and shaped the greatest intellectual achievements in human history, is incomplete in ways that go all the way down, not just missing some pieces, structured wrongly, at a level so fundamental that finding the right structure will require a kind of thinking that has not yet been done. When Copernicus looked at the night sky and realized that the stars were not rotating around a fixed Earth, but that the Earth was rotating and revolving around the sun, the sky did not change. The stars were exactly where they had always been. The planets moved as they had always moved. Nothing in the visible world was different from one day to the next. And yet everything was different because the framework through which those observations were understood had changed completely. The same observations, the same data, the same phenomena, but a different structure, a different picture, a different story about what was actually happening. The revolution was not in the sky, it was in the mind. And when the next great revolution comes, when someone finds the framework that makes sense of the Hubble tension, and the dark matter, and the emergent space-time, and the observer-dependent reality, and the missing 95%, the revolution will not be in the universe. The universe will be exactly as it always has been, doing exactly what it has always done. The revolution will be in how we see it, in the conceptual structure we use to interpret what we see. And that revolution will change everything. Not everything in the sense that your daily life will be unrecognizable. Not everything in the practical sense of how you navigate your world, but everything in the deeper sense, everything in the sense that matters most, the sense in which Copernicus changed everything and Darwin changed everything and Einstein changed everything, the sense in which your understanding of what you are, where you are, what kind of thing the universe is and what your relationship to it is, all of that will change. The picture of yourself as a solid, continuous, causally connected being moving through a fixed 3-dimensional space under a universal time, a picture that feels so directly, so undeniably given by experience, will be revealed, as it is already being revealed by the science we have described, to be an approximation. A good approximation, a useful approximation, an approximation that will continue to serve you well in all the practical dimensions of your life, but an approximation, a shadow, a high-level description of something that, at its most fundamental level, is stranger and deeper and more surprising than anything your evolved, survival-oriented, macroscopic, world-calibrated brain was built to directly grasp. And here is where we must stop, not because the story is over. The story is not over, cannot be over, may never be over in the way we expect endings to work, but because the next step in the story has not yet been taken. The data is in, the anomalies are real, the cracks are visible, the framework is straining, but the new framework has not arrived. The new picture of reality, the deeper, truer, more fundamental description of what the universe actually is, has not been written. It is being worked on right now in theoretical physics departments and at chalkboards and in the small hours of the morning, when a physicist stares at an equation that almost makes sense and feels the presence of something just beyond the reach of current understanding. It will be written, eventually, probably, and when it is, you will have been here, in this particular moment of history, this particular window of time, when the old picture was visibly breaking apart and the new one had not yet appeared. You will have been alive in the interval between certainty and the next certainty, in the space where everything that seemed solid has begun to dissolve and what will replace it is not yet visible. This is not a comfortable place to be, but it is an honest one. And right now, in the landscape of human knowledge, it is the only honest place there is. The universe does not owe you an explanation. It does not owe you clarity or comfort or a picture of itself that your mind can fully grasp. It has been doing what it does for 13.5 billion years without asking whether its behavior is comprehensible to the particular form of organized matter that evolved the capacity for comprehension on one of its smaller rocks. What the scientists who are confronting these anomalies are discovering, slowly, reluctantly, with the kind of intellectual courage that real science at its best demands, is that the universe's behavior is not, at its deepest levels, readily comprehensible, not because it is random or chaotic or lawless, precisely because its laws, its structure, its deepest nature, are of a kind that the human mind, evolved for a particular kind of world, operating with a particular kind of cognitive toolkit, is not naturally equipped to see. The universe is not hiding from us. We are simply not yet shaped to see it clearly. And the question that hangs in the air, unanswered, is whether we ever will be. Whether the gap between the kind of mind we are and the kind of reality we are embedded in can ever be fully bridged. Whether the truth, the real, deep, fundamental truth of what exists and why and how, is something that a mind like yours, in a body like yours, on a planet like this, in a moment like this, can ever actually reach. That question does not have an answer yet. That question may not have an answer for a very long time. And until it does, the room around you, solid as it seems, familiar as it feels, real as it undeniably appears, rests on a foundation that no one, anywhere, fully understands.